Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, it's a pleasure and honor to introduce Roger Vallour. To me, he is my advisor. He was an excellent advisor, but to the world, he is, of course, a very respected researcher. So he's probably best known for his contributions in the area of timed automata, which led to the whole area of hybrid systems. But he has done a very impressive breadth of work. So there's very different areas where he has published very interesting work. And what I like a lot about his work personally is that he has always very solid theory, but never forgets the application. So I think that's a very good qualification to have. So Rajiv.
So thanks, Sebastian. So it's great to be here. And so in the morning I was talking to Tom, and he told me about all the projects that are going on here and the breadth of areas being covered. So this has really become the center of the world for formal methods. So it's good to be here. So today I'm going to tell you about some work we are doing on how to check for confidentiality. And this is the thesis work of Pavol Cerny, who is a PhD student at Penn, and he's finishing. In fact, he had the thesis defense only last week, and most of its slides are his slides. So privacy is of increasing concern to everyone in this networked world. People are storing all kinds of information on their computers, and also increasingly more and more on their cell phones, and using it for online banking, for health records. And every time you do any transaction, you're worried about, is it leaking the confidential data that I want to keep private? And that's a big concern. And it's not just a hypothetical concern, but these are various headlines from last few months where the society in general and the governments also are increasingly worried about confidentiality of data. So what do we specifically focus on in our study? It's how programs can leak data maliciously. And in particular, we have been looking at these apps called midlets. So these are Java applications written for the Java micro edition, which is a restricted version of Java. And you can download these programs onto your cell phone. What we want to do is to check whether these programs are leaking data or not. Right? And as this says here, that most of the compromises of confidentiality are from unauthorized use of data. Of course, you want these applications to access the data. So for example, you have address book on your cell phone, and if you have an app which deals with the address book, it has a legitimate reason to access the address book. But then there are some other uses which are not authorized. So how can we differentiate between authorized users and illegitimate users? And that's sort of the goal for this talk. So here is a simple example where here is what's called this midlet, which is really a Java program. So it's this event sharing midlet. So it's enhancing the features of your mobile phone, this app, by letting you organize events. And to organize that event, it's accessing this PIM, which is the Personal Information Management system on your cell phone, and then it accesses the phone's native data, and then it sends a message. So what we are going to assume is that we want to prove that whether the information leaks or not, and what we are going to assume is that the adversary or the attacker knows the program, because these programs are downloaded from a publicly available site, or maybe it's the vendor who is providing these apps who has put some malicious code in there to extract your information illegally. And the adversary also gets to listen to the messages. So that's what the observer observes. So the attacker knows the program and observes all external communication, and something illegal would be before sending the message, the app does some useful work, but then it's encoding the information in some secret message. So for example, suppose the attacker wants to know whether this particular phone number 555 is in your phone book or not, and you want to keep it private. You don't want others to know whether you have that number in your phone book or not, right? So there could be a malicious program which checks whether this message is there or not, and then sends that information out. So what we want to focus on is a program analysis tool which takes the program and the information you want to keep secret and certifies the program. Now, currently there are actually some agencies which would certify these apps. So they would say that this app is it's keeping your data confidential. But if you actually look at what they do, they are just registering these apps so that later if there is some problem and if you have a complaint, they can go back to the registry and try to find out who had written that app. But there is no real analysis done. So it's just a registration service. So the information is leaked due to malicious code, and this will become more clear later when I formally define what we mean by confidentiality. Is that confidentiality is not a property of a single execution. So if you look at this particular execution where the value of low may be 0 or 1, that doesn't really tell you whether that phone book is in that whether the phone book contains that phone number or not. It's really the analysis which talks about equivalent runs, what could have happened, the inference drawn from a single execution that leaks the secret. Well, I mean, what it's really telling you is, so there is some inference going on. So in this case, the value of low, it's just leaking the information about low, and you have to infer that from that phone books. Actually, this point would become clear if I maybe from this example. So the question. So here is another example where here is another application where you first get the phone number from the user, and then you so the user selects some entry, and then you consult the phone book to get the number, and then before actually sending the message, you check whether the number is valid or not. If the number is not valid, then it outputs error, and then you input the message from the user and then send the message to that number. Okay, and so this is actually a legal thing. So we want to yeah.
So can you say that, in answer to Yuri's question, what it probably means is that in order to show a counterexample to confidentiality, you cannot simply give a single trace.
So the definition of confidentiality is not it's not a property of a single trace. You have to say that something is secret if for every execution there is an equivalent execution. Equivalent means the observer sees the same messages, such that in one execution the address book contains the secret phone number, and in another execution the address book does not contain the secret phone number.
There is a property of two traces or something?
Well, in general, it can be more, yeah. So for example, I could say that I don't want to reveal my bit until someone else has revealed his or her bit. So in that case, you would need more executions, because it's like an until property, and whether something is revealed or not requires you reasoning about equivalent executions, but then there is this temporal aspect, so you have to switch. Okay, so the question is, how do we, with the existing technology, how would we do something like this? So there are two main strands of research. One is called taint analysis in program analysis literature, and so you want to check which you want to check whether the message that you are sending, does it depend on phone book or not. And you can do a simple variable dependency analysis. And if the message is not dependent on phone book, you could conclude that the phone book is not tainted. The sending of the message does not taint the phone book, and hence everything in phone book is secret. But in this example, as you can see that the taint analysis fails, it would say that the phone book is tainted, even though this seems like a valid code. And so what's happening is that since the number depends on phone book, you have a dependency. So number depends on phone book. And then you have this test, that whether the number is valid or not. And in this case, it's not a malicious test. It's not checking whether, it's not checking some other property of the phone book that we don't want it to check. It's just checking whether the number is valid or not. But since the sending of the message is in the conditional that involves number, the variable dependency analysis will declare message depends on the test involves the number, and number depends on phone book, so message depends on phone book. So the taint analysis would declare this to be malicious, and what we are really interested in is certifying this to be correct. Right? Now there is another, yeah.
The analysis, on the other hand, will be also not strict enough. For example, in this case, in the previous example,
Yeah.
you want to send a bit 1 or 0.
Yeah.
So the attacker can instead just send, for example, 10 bytes versus 10K packets to communicate with the other guy whether this is a 1 or 0. If it is 1, it sends 10 bytes. Otherwise, it sends 10K. So in that case,
That's also possible. And so there is also this language-based approach. So there is this whole literature on information flow, and people have developed specialized programming languages, type systems, which enforce integrity and confidentiality constraints. But all of them work at the level of variables. So the basic concept is, does this variable depend on this? And you could, in this tools like GIF, which is for information flow for Java, you can annotate variables with extra type declarations, and it would then keep track of the dependency between variables, do type inference. And now there is this concept of downgrading, which would the user could annotate this condition as being harmless, and that would make the type system declare that this is actually an okay test. So, but that would require user intervention, and in fact the user would have to add extra type annotations for this program to work.
Downgrading business is an escape hatch. In general, it could be unsound, right?
It could be unsound, right? Yeah. Right. Yeah.
Okay.
Okay, so that's sort of motivated us to look at trying to apply more finer analysis techniques like model checking, which would check the exact values of various variables. Yeah.
Does the user specify a source and a sink, and the problem is to infer whether there is some dependency between the source and the sink, or what is the information leak problem in general?
Oh, so I will give you one specific instance of the problem that we analyze. Yeah, but in the literature, if you look at information flow, there are many variations of this. So in the programming languages, in program analysis, and they all have similar goals, but one needs to formalize the problem, and I'll pick one particular definition in a minute. So what we are going to do is to use something like software model checking, where you have a program and then you do some abstraction, but you have a specification. So we have a specification-driven analysis, and then the checker would analyze the program with respect to the specification. And so of course this has been quite popular in tools like SLAM. Now one would we have already talked about these equivalent executions, but that's the reason why you can't really apply a tool like SLAM immediately. And so it's not so more formally what it means is that you cannot specify confidentiality in logics like, say, linear temporal logic or you cannot express it using monitors. You cannot express it even in branching time logics or mu calculus. Because the fundamental definition really talks about equivalence of executions, which is just not there in these executions.
Is it similar to the business with sequential, the definition of sequential consistency? There's also this notion of equivalence, and there's this for all exists going on there also.
So it has that flavor. So actually, it's but in terms of logics people have studied, it's closest to logics of knowledge. Okay. You could say what does the attacker know, and you know something if in all worlds that you consider are possible based on your observation, the same property holds. Then you know the fact. Yeah.
So can't you like transform the program to some other program, and then this property would become
not really. I mean, I think in some special cases you can, and actually there was some work by Alex Eichen and his student on looking at some specific information flow property where you do this program composition and you run 2 copies of the program, but that's not always possible. Yeah. Yeah.
I wonder, I mean, your first point here, confidentiality is not the property of a single execution,
Yeah.
but model checking does not check a single execution. It verifies all of them.
That's a good point. But the specification language, if you look at the how do you define semantics of, say, a monitor that you would write in the specification language of SLAM? It would be a single execution satisfies the monitor or not. And now the checker is checking whether all executions satisfy that. But it's not expressible actually. So it's so I guess this is a bit confusing. But it's not specifiable in LTL and it's not specifiable in mu calculus. That's a precise statement. Yeah.
So would it be equivalent to trying to decide observational equivalence of 2 versions of the program?
Not really, no. I don't think so, yeah. So in fact, the notion of refinement also has to be changed, yeah. So I think there is this for all there exists quantifier. And so so techniques based on, say, just over approximations or refinement are not going to work, yeah. Yeah.
I heard there is a formal definition called non-interference,
Yes.
which seems to cover security and privacy. So I don't know whether...
Right. So non-interference would fall in this general framework, yeah. So I mean, I'll give you a specific definition, and maybe then I can tell you how non-interference is different from this, yeah. But I think the general analysis method that we have would work for the non-interference definitions also. So in non-interference, there are low variables and high variables, and the program is safe if by observing the values of low variables, you cannot infer anything about the high variables. That's that also has a similar flavor. So I guess all of you know tools like SLAM, where what you first do is you do over approximation. So just doing over approximation in this case and proving property of that abstracted program won't be, it just wouldn't make sense in this setting. And also what we're really interested in is verifying programs, because finding bugs is not particularly interesting in this setting, because we don't even know what these applications are. These are not really safety critical applications, but when you download something, you just want a guarantee that it's correct. So what we want really is that this tool which takes the program and the specification, hopefully the specification had some generic pattern so that the user wouldn't really have to write this, but we haven't thought about how to really use this in practice, and then the tool would say yes or no. And what my talk is going to do is, in the first, maybe for the next 10 minutes, I'll tell you a bit more about formal definitions of specifications, and then in the bulk of my talk, I would focus on the analysis method for the Java programs. So just to give you the context, in standard verification, sort of the basic for safety verification, the basic problem is really like reachability in this large graph whose nodes correspond to states of the system. And then if you want to write properties about sequence of events. People have developed variety of temporal logics, and the basic complexity is well understood. And then for general programs, of course, this problem is undecidable, and the over approximation but is a sound method. And in my talk, I'm first going to tell you about what's the formal definition of this confidentiality. I'll give you a brief overview of some theoretical results we have in terms of what would be the right temporal logics and what would be the basic complexity for the finite state systems. And then the bulk of my talk would be on how would you actually build a program verification tool for these kinds of properties. So okay, so now here is the more towards a precise definition. So to define this notion formally, we need three concepts. One is secret. So this is just a property over states. You could say, is this phone number in my address book? That would be secret. So it's not at the level of variables. It's at the level of properties, predicates over variables. Then we need a notion of observation. What does the observer see? And in most settings, it's sort of natural. You could say the observer sees the messages that are sent. You could say that the observer sees the output of the program. Or you could say that, well, it's really an infinite execution. At every step, the observer gets to see some subset of the propositions. And then the observation is just a sequence of observable variables. Right? And two runs are equivalent if they have the same observation. And then we also need this condition. So what I'm going to define is that for all executions satisfying the condition, the secret is not leaked. So this is really required because I'll show you later examples where this precondition is really necessary. So these are the executions of interest. So for example, if I'm searching for a particular phone in my address book, then of course from what the app does, the information about that specific number is leaked. So the property you would prove is the condition would be as long as the phone number you're searching from is not equal to, say, your friend's number, that should not be leaked. So that's how that con plays into it.
The definition of the secret, you say, is a predicate over the
Yeah, secret is it's a state.
But that's a constant over the execution of the program.
Yeah, so this definition is really the generalization of what you would call like a safety property for programs. So safety property or invariance is that this is a property of state over state variables, and it should hold in all reachable states. So the analog of that is this conditional confidentiality, says that for every execution satisfying the condition, there exists an executions R prime such that R and R prime have same observation and they differ on the values of secret.
So con and secret are predicates over entire executions.
They could be predicates over entire executions or could be over states, right? Yeah. So cond is a subset of executions, and secret typically is just it's a property over states, right? Yeah, but could be over executions. Okay, and so the intuition is that the secret is not leaked if for every interesting execution there is an equivalent one which has the same observation but have different values of secret. So by observing this execution, the observer cannot conclude whether secret holds or not.
So the difference between this and some of the other definitions kicking around is that you're going to make observations all throughout the trace as opposed to just in the post state.
Right. You can make observations all throughout the state, and also the secret is really a property of variables. So you could say, is x greater than 5? Is that a secret or not? And typically in language-based security, it's more about variables. Are these variables secret or not? Yeah.
So I mean, with verification, you could do it, right? So, but then or at least, but it's only been done, I think, in the when you look at the post state, not that observations all throughout.
Yeah. So in fact, actually, in the examples we have done, we really have we have a special variable in which we collect the observations, and the and then you just reason about that. So in the end, it will be putting together components like weakest precondition computation, loop unrolling, and invariance, and so on. So when I show you this.
If you just collect all the observations into a variable, I mean, if you call that variable low variable, then could you not use existing techniques, including existing techniques that work with weakest preconditions?
So the okay, maybe when I show you the solution, you can say I don't think there are existing techniques. I mean, we are just combining existing techniques. So in the sense, it's not like a new technique, but it's I'm not aware of any tool or which actually does
I have a
this.
feeling that Rustam is driving at the following point.
Yeah.
Let me just say it. I think what you're saying is that Rajiv is making two contributions. One is in the definition of the specification, and that is completely independent of whatever technique you use to actually verify that specification. You could use model checking if you wish. You could maybe extend type systems. Maybe you could use weakest precondition and verification tools. And then you will propose one particular way of checking that specification, which is based on some model checking stuff. Am I right?
Well, it involves it combines the various things, right? Yeah. But it's not the standard weakest precondition. There is this quantifier alternation. Okay, so I mean, you're checking a different property, right? Yeah, it's I'm not in
contributions. We have stated a particular
Right,
property, and then I can go off and do
sure,
precondition,
right,
whatever, right? Yeah. Okay.
So I'm worried about this secret. Secret is a property on variable.
Yeah.
So I consider my program, it has 17 variables.
Yeah.
7 of them satisfy the property.
Oh no, the user specified secret. So you could say that is the predicate x greater than 5. Is it secret for this program or not? Then you know if I prove that x greater than 5 is a secret of this program, then what the guarantee is that by observing the program executions and knowing the program source code, the attacker won't be able to figure out whether x is greater than 5.
Can it be that x greater than 5 is secret, but x prime greater than y prime is not secret?
Yes, that can happen.
And
then you would have to check, because you would have to check a different property, basically.
That seems very strange. And the renaming of variables, even bound variables, may influence what the secret is.
Yeah, I mean, it's really, but that's same as saying that if I prove x greater than 5 is an invariant of my program, I wouldn't know whether x prime greater than y prime is invariant or not, right? You would have to check whether that x prime greater than y prime is invariant or not. So in fact, in this non-interference, they say if there is a quantifier where all properties involving x and y are secret. That you could infer something like that, but then. But it's in most cases that is too coarse, because some information about x and y is being leaked. Yeah.
And I'm also trying to get to the bottom of why you generalize secret as a property of the execution. So could I do this equivalently by talking about the secret bit that is set at the beginning of the execution and never changes?
Yeah.
And that is the secret. And then maybe tie that secret to the rest of the execution using the condition.
Yeah, it's possible. Yeah. Every time something, I mean, that property could be encoded as a Boolean variable. Yeah. If you say x greater than 5, or whether 555 is in my address book or not, that could be. I mean, that property itself could be a bit which you set at the beginning based on your inputs, yeah.
Let's see, the second you say this 5555 is in my book.
Yeah.
It is not a variable. Which variable?
No, you would have to introduce, so we don't really introduce it, but we could change the program so that there is a new Boolean variable in the augmented program whose value reflects the secret. And then, it would be about that bit. Yeah.
So, how is observation defined?
So the observation is would be the sequence of messages the observer sees, for example.
So it's another condition, predicate, or?
No. So actually in our tool, really there is we take the original program, we augment it with additional variable which keeps track of the observation.
Okay.
And the value of that, so two executions are equivalent if the value of that variable is the same. So that variable could collect all the messages sent or output.
And this is different than con. The condition con.
Yeah, that's different. Yeah, that just says that the we want to look at these executions where the number you are searching for is not equal to 555. That would be gone. Because on those, if you're really searching for 555, then whether that's in your address book or not would be leaked. Yeah.
So, but it seems like the condition is just a parameter. It's not fundamental in 1 and 2, right? I mean, what's fundamental?
It just I mean.
Just a condition on the executions.
Yeah, it restricts the set of executions you want to look at. Yeah.
If I have a password guessing program,
Yeah.
what would it be would it be classified as confidential or not? So the password guessing program works like this: it takes an input n as an integer input n,
Yeah.
and then tries all the first n possible combinations of characters. So let's say that the password is like fits within 16 bits.
Yeah.
So it tries out all the possible first n combinations of bits. So for some value of n, it will reveal the secret. For some value of n, it will not reveal the secret.
The password guessing program, is it? It's. I guess that would. Yeah, I mean that would. So the execution which actually guesses the password correctly, for that the secret would be leaked. So it would be tagged as not correct. I mean, it is revealing the secret.
And what about the password checking program?
Oh, the password checking program should be. Okay, so in fact, that's a good example. So the condition would be what you enter is not equal to password. See, for what you enter is, if it's not equal to password, it will not leak the password. But if it's equal to password, then it could leak that. Yeah. So then, for all executions where what the user entered is not the password, the response that you get back is not revealing the secret, which is the password.
In that case, if the length of the password is short, then every time of a failed attempt does reveal some information. So at least this fails, and then if you iterate on
yeah, so there is so that's a separate issue. What happens if you run the program multiple times? Can you collectively infer something? That's not handled by this definition. Another thing which is not handled is really probabilistic things. So in the non-interference literature, people worry about probabilistic settings where, so what may happen is that for execution that you observe, there may be an equivalent execution where the value of secret is different, but the probability of that equivalent execution may be very small. So you may be able to infer something with very high probability, and we don't handle that because doing any probabilistic reasoning is challenging. Okay, so let me tell you briefly, maybe in like 5 minutes, about if you wanted to generalize this to temporal logics, how would you do it? So, and the motivation is that you want to talk about things like the orders in which secrets are revealed. So it's not that you don't want secret shouldn't be revealed, but it should not be revealed unless someone else tells you something. So since we want to talk about multiple executions, the classical thing you may want to think about is trees. A tree has all the executions, right? And but of course, the standard branching time logics are not adequate. So this mu calculus cannot be specified. So what we have is actually this model of label tree. So a path through the tree is a program execution. And for now, let's assume that the notion of observation is by observing the value of some proposition. So agent A is observing the value of proposition P. So at this point, for example, the agent A knows that the value of P changed from, it was P bar, P, and then P bar. So it knows the sequence of P's that got you to this state. So what we do is we augment this tree to give the semantics to these kinds of logics. So we define these enriched models, so a tree enriched with the jump edges or equivalence edges. So here there is an A-labeled edge between these two nodes because the history or the knowledge of A here is same as the knowledge of A here. It's in both cases the A had seen P bar P, and here also it has seen P bar P. Or for example here B is observing Q. So at this point B had seen Q Q Q. At this point also it has seen Q Q Q. So you add a labeled edge between two nodes if the observation of the execution leading to those two nodes is the same. And so now you have now a tree becomes more like a graph. And on this graph you can just define logics like in mu calculus or CTL. In particular, this logic that we defined and studied has this extra operator, which is this says that there exists a state such that which is inequivalent, which is indistinguishable according to A, and so F holds there. So for example, at this point, the EX is the standard next time operator in CTL. It's existential next F. So it just says that there is an F successor in the tree by executing a step of the system. And this says that there is a possible world where G holds according to the knowledge of A. It's indistinguishable according to A.
What is this I?
I is indistinguishable, right? So E and A existent for all, and I is it's indistinguishable according to an agent. And so you can define this for multi-agent systems, and you can then, for example, define a property like confidentiality, which says in all reachable states there is a world in which is okay according to A where alpha holds, and there is a world which is possible according to A where alpha doesn't hold. So that's something being secret. Now, if you say that this secret holds until B reveals Y. So B revealing Y just means that in all worlds that B things are plausible, Y holds, or in all worlds that B things are plausible, Y doesn't hold. So this is just a negation of this. And you can nest these kinds of formulas and study them. So that we have some interesting theoretical results about this, but I'm just going to just tell you that if there is no nesting of these indistinguishability operators, then the complexity is reasonable. It's exponential for both CTL and mu. But if you allow nesting of these quantifiers, then for CTL it becomes non-elementary, and for mu calculus it becomes undecidable. But both these formulas that we saw here, they don't really have nesting of these, there is no nesting of these jump operators. So nesting would be, for example, here inside this EIA, this formula X here itself was complicated, and it itself involved a reference to one of these jumps. Yeah?
So for two states to be equivalent with this definition, they have to be at the same distance from the root node?
Right. But there is one can imagine a time insensitive version of it, where you just look at the order in which the propositions have changed and not how many times P held true. And one can handle those also. So this is really like time sensitive version, where you know how many steps the system has taken, which is actually not a reasonable thing in multi-agent systems. Okay, so now what I really want to focus on is the how does one do this in practice. Actually, these trees here I think are actually interesting, and people are looking at what would be just looking at some theory of these trees. So you have a richer structure than trees, and under what circumstances you would get decidable logics. There's some good connections to automata, and so those are some interesting theoretical problems.
What would be a natural example when you want to nest this EI?
Oh, nest. Yeah. Yeah. So I think nesting. I don't know. I think this is really the example where just one is not enough, which is this seems like a natural property. Yeah, but this doesn't involve nesting. So this is our motivation for looking at sort of temporal sequencing of these. But that's the same thing as if with untils, thinking of properties with nested untils is kind of hard, yeah. So, okay, so now let's go back to programs, and in fact, to make things simpler, I'm even going to get rid of Java syntax and make it a simple array, and make it actually quite simple. So here we are looking for a key in an array, and so the input to this program is the array A and the key. And by changing the value of A and key, you get different executions of the program. And what this program is doing is that the result would be either -1 if the key is not in the array, and the result would be equal to the key if the key is in the array. And it's a simple loop over the program. And so we want to know whether this is secret. So whether A contains 7 or not. Right? So in general, I don't want someone to send information about this thing when I'm searching through my address book. Okay. So our secret would be now this predicate, whether A contains 7. Now in this case, the observer is just seeing the value of result. So the value of this result would be the observation, and the condition is key is not 7. Because if key is 7, then of course by a legitimate execution of this program, the value of this predicate will be leaked. Okay. So now the property we want to prove is that for all observations, if H is valid, which means the key is not 7, then the observation is consistent with a state where secret holds, and it's consistent with a state where the secret does not hold, which means there is a value of A and key where this holds, and value of A and key where this doesn't hold. And actually this program does satisfy the conditional confidentiality, because if say the observer sees 3, then there is a value of A and key for which key is not 7. So this observation is one where I do want to analyze the program, and for this observation there is a value of the array where 7 is there, and value of the array where 7 is not there. So if I see 3, I cannot infer whether 7 is in the array or not. So how do we solve it? So we try to compute the set of reachable states here. We try to think of at least the set of reachable states here. Then my condition is basically going to be if there exists a state that's reachable, which satisfies the condition, which this is the condition, and the value of result in S is H, which is this is a quantifier over all possible values of result. And so this says, for example, here a state where secret does not hold is just saying that there is a reachable state where S does not satisfy the secret, and the value of result in S is the same H. So of course computing the set of reachable states is not a particularly smart thing to do. Yeah?
In the previous example, what is the motivation behind this condition? Like, are you preventing the user to run this code with key equals 7? Like, how is this condition really enforced, or what is the motivation behind having this condition in real life?
No, so the motivation is that I'm looking for, so forget about these things here. So suppose you just look at this program, right? And what do you want to prove? You want to prove that if I'm looking for a particular key, the information this program sends should only reveal about whether that key is in the array or not. And for some key prime which is not equal to key, it should not reveal whether key prime is in the array or not. Now, if this program was malicious, and if there was a condition here which also checked, in addition to this, had another loop which checked whether 7 is in the array or not, and if the 7 was not in the array, so this was like an AND of those two conditions, right? Then by observing this result, the attacker would be able to infer something about you were not looking for. Now, to formalize this, we say, okay, let's say our secret is A contains some specific value. And this is because we don't have, in our analysis, we don't allow quantifiers in these conditions. In fact, if we have, so I will come to that later, the extensions we would want to do is to make the language for secret richer, and in which case maybe we could simplify some of these things. So what we are really doing is setting this to be a specific value, A contains 7, but then this is not going to be a secret if the key was actually 7. So that requires us to restrict the set of executions we look at. Okay, so now so instead of computing R, now we are going to compute two things. One is the over approximation R plus of this set, and an under approximation R minus. And why do we need two things? Because for this quantifier, for all possible observations, a safe thing to do would be to over approximate. But once we have looked at that, to show that in fact there are executions where secret holds and secret doesn't hold, we need under approximations. We need a concrete executions, the executions which are guaranteed to exist here. And here I'm going to use R minus, here I'm going to use R plus, which is fairly natural. So basically the formula we want to now check is there exists a state in R plus such that, so I want to look at all observations such that it's consistent with some state in R plus, and then I want to show that there is a state in R minus where secret holds and a state in R minus where secret doesn't hold, and the value of H is that. Okay, so, and it's easy that this, if I can establish this, I know the program satisfies confidentiality.
So don't you want to take the over and under approximation of the set of executions and not the set of states in this case?
Well, of course, this is an approximate solution, right? Yeah. So in fact, in all our examples, we are going to introduce, do an automatic annotation of the program where this variable called result collects all the observations that you want to observe. Yeah. So basically, as you would expect, we are trying to move from this temporal thing about executions to something that involves computing with invariants, preconditions, and so on. And our goal is to use yikes in the end, right? Yeah.
Z3.
Z3.
You have to be politically correct.
Leo doesn't care.
Oh.
Okay, so the first thing which in principle could be done automatically, but in our current tool the user has to provide this. So how do you compute the over approximation? So in this case it would be an invariant at this point, right? So this would be any invariant of the program could act as an over approximation. So for example, for this program, this result is equal to key or result is -1 is an invariant. And this actually works for this particular example. Under approximation, we do loop unrolling. So so you take this program here, the loop is unrolled twice. And so now you know that any execution of this is a concrete execution. And that's what we would do to do under approximation. So this assume here just make sure that in fact we are getting out of the while loop.
Actually, this way of computing under approximation is not going to work if the witness execution depends on the input, right? Because then you might have to unroll, as you increase the input, you might have to unroll the loop lots and lots of times. So there might not be any upper bound on the under approximation.
Right, yeah. So in fact, I mean, as you said earlier, that the solution here particularly is, I mean, it's fairly basic, and one could replace these blocks for computing invariants, for creating under approximations by all the wonderful tools that you guys have been developing, right? Yeah. So now you probably have already guessed this. Now this all becomes actually a logical formula. It's for all H. So you're not really computing the set of reachable states. It's really, so this is, if I just have a quantifier over all the program variables such that the invariant is satisfied, the condition is satisfied, and the result is equal to H. The other thing that we need is this under approximation of the program, and then once you have the under approximation, you need to compute the weakest precondition, because so the weakest precondition of the program with respect to secret, the secret holds at the end, and the result is equal to h. So this is, we are quantifying over all possible observations, right? And the other thing is similar. Like here you compute the weakest precondition with respect to not secret, and result is equal to h. Right, so now this becomes a formula like this, and for the class of programs we have, we can actually compute the weakest precondition, and this then is given to
You're assuming deterministic programs here.
So here these are deterministic programs.
So getting the weakest precondition here would give you a condition that's too strong actually if it's non-deterministic programs. But if it's all deterministic, then
yeah. So well, I mean the only non-determinism here is in the input values. No, you are computing weakest precondition for the under approximation, which is obtained by loop unrolling. So that's not causing any abstraction. I mean, the invariant is really the abstraction.
So what do you mean by loop unrolling? You can unroll the loops completely.
Oh no, so it's just a hack, right? I mean here so we give so here the loop is unrolled twice, but actually what you really want to show is that there is an execution where the secret holds, and for most of the examples we have dealt with are of this form, that whether some value is in the address book or not, and for those settings it's enough to look at address books of size 2 or size 3, and that size tells you how many times you need to unroll the loop. So, but as Shad said, I mean, one could construct examples where such bounded number of unrolling a priori may not work, right? Yeah. But the good news is that the midlets, I mean, so the programs we have checked, I mean, we didn't really create them. They are from the web, and these are simple methods. Typically, we have analyzed individual methods and 100 lines of code, and they're fairly simple. I mean, they are not doing anything complicated. They are just going through your address book, typically, searching for something.
You didn't show how to deal with procedure calls, but it would be something similar. When you are doing the over approximation, you would work with pre and post conditions, and when you are doing the under approximation, you would just inline calls, right?
Yeah, right. Yeah. So but the current tools. So the main sort of the limitations of the current tools are we just analyze individual methods. Okay. The user has to provide this invariant, which I think in theory could be calculated by an automatic tool. And this under approximation, the only method we have for under approximation is the user specifies a bound a priori statically, and then we use that as a bound on the length of these data structures and compute a simple bound on how many times the loop has to be unrolled. Yeah. And then do the weakest precondition computation. Yeah.
You don't consider timing channels, right? Or is it weakest liberal preconditions? Or?
Yes. Okay, but there is still one. We can do slightly better. There is something interesting I can tell you. One is that there is a quantifier alternation here, and all tools would basically, even for simple programs like 10-line programs, they would just die on something like this, right? So what you really want to do is to get rid of this existential quantifier. Right? You want to get rid of the quantifier alternation. And there is a simple observation here. So for most of these programs, even though they're talking about this data structure, the only way you are accessing data is through equality tests or by order. Right? I mean, you are not doing any complicated arithmetic on the addresses. You are just checking whether the key is equal to the some entry or not, right? Or maybe it's sorted and you're looking at ordered things. And so for this program, if you look at this,
When you do I++, right?
oh no, but that's just an iterator over the array or over the address book. Oh, I'm looking at the entries of the array, right? Yeah. So this.
Oh, okay. You're saying that the data contained in the array you don't do arithmetic on.
Yeah.
You can do arithmetic on the index variable.
Oh yeah. So the index variables could be anything that your tool can handle, right? Yeah. So the or the message. I mean the message that you send, and so on those things you are not typically doing any arithmetic. So it's really on the observations. You are not, the observations is not from a finite set. It could be any entry in your address book or could be any number. So there is no a priori bound. But on those observations, you are not doing arithmetic. So here, so for this, for example, the result was our observation. So you can see that the only interesting values of result are -1, okay, and it could be key, the value of the key, and the or it could be some other value. So for this, for these kinds of programs, we can actually prove that the you need a constant number. You need to check only constant number of values. So in particular for this, it's since our condition was that the key not equal to 7, and the secret was whether the array contains 7. 7 is an interesting value. So 7 comes from the values that are mentioned in the secret and con. -1 comes from the program because it uses that as a constant, and then you need one other value. Yeah.
You know about these algorithms about data independence, scalar sets, etc. It's a bit reminiscent of that.
Yeah, right. And so in fact, so the people have looked at various special cases of, say, the theories of arrays where the only test you can do is equality and so on. Or if it's order, then it becomes a little more complex because then so you would need a value greater than 7, a value between 7 and -1, a value less than -1, but still it's a finite number of values which could be computed statically.
Don't we look at code, the locality code? We have 425, so they can look only part of your address book. Starts from 425 from array code.
Okay.
So they may, in addition to, it's not just apples because they can distinguish.
That's that's a good point. Yeah. So that's that could be handled, but yeah, we haven't looked at that. Yeah. So you have like partial matches, or you can think of keys as records, and you are doing queries on parts of the record. Yeah.
So, Rajiv, I'm still trying to understand this restriction here. How would you state this property if you were thinking in terms of first order logic? So this is a first order logic formula, right? If you ignore that you're doing arithmetic over the iterators, right? So so in first order logic you just have equalities and no other predicate. So you have just function symbols and equality.
Yeah.
Then is your result something like that for those kinds of first order logic formulas things are decidable and you just need a finite number of finite size models?
Yeah, no, so actually it's not about decidability, right? So it's just saying that if you have existential quantifier, and if you look at this formula, so this and if the so we are actually getting rid of this universal quantifier here, right, for all h, and if you look at how h is used inside this formula. So it's compared with this history, which is really the observation. And now you have to now look at the program, and from the program, if you would conclude that the only way this result gets updated is through equality, and so this equality is so here it's being assigned to AI. So you need to look at now how the elements of the array are accessed. Now if you look at how these elements are accessed, it's through an equality test. And they are not being updated, and you are not doing any arithmetic on A. So that's the condition. Yeah. So you start with your observation, find all the variables that observation variable depends on, and you prove that for all those variables, all the assignments and the conditionals involve only equality tests. And if your program has that property, then you look at all the constants that are mentioned in that program and the constants that are mentioned in the specification, and those constants plus 1 is the size of the domain. So then so basically then you can get rid of that quantifier, and then it becomes then it becomes a satisfiability problem, where you just have an AND for all the values for H, all this finite number of values of H you have computed. So the tool basically takes Java bytecode, and this Vala is some it's a tool that processes Java bytecode and creates some intermediate form. And so this is the tool that Pavol built. So the user has to specify secret and const. Those are the predicates, and then the invariant which the user has to supply. And this is used for the under approximation, and then it generates this formula, and we give it to this tool. And so the typically things we have checked are these Java methods and things which are methods which are used for managing contacts or calendars, to-do lists, and so on. You can also we have also checked things like array libraries and vector libraries, and so typically, these are small methods, maybe 100 lines, even fewer in many cases. And the number of loop unrollings for these things turns out to be small, so you can just do it with a couple of unrollings, and you don't really need much time. So these were actually, and most of these things are correct. I mean, but we added some malicious checks, and then the tool does find it, like in these cases.
And all of them you specify the loop invariant manually?
Yes. Yeah.
So you're not really doing model checking?
It's not really model checking. Yeah, well, whatever it is. Yeah, some program analysis too, right? Yeah. Okay. Okay, so basically, so I think so this is sort of, I think I think people haven't really looked at this problem in verification model checking type community. It's mostly done in this language-based security community, but I think using specifications and using specification-driven reasonably automated analysis can be a good way of certifying these programs. They're small, and you could make sure that they are correct. So as many issues came up during the talk, so there are many ways in which we could improve this. So we don't handle multiple methods calling other methods. If you look at this tool, many of these. So this is actually, with the use that I started with, the user supplying secret and const is really not the way to go about it. But in most of these things, they are very generic patterns. So when someone registers an app, so instead of just registering it, maybe the repository actually had some built-in tests for some typical things that the app could be leaking, and it could check for those. These are again could be improved with better program analysis techniques. Yeah.
So you mentioned that if you make the language of secret richer with quantifiers, then maybe you can get rid of the condition in some cases.
Maybe you can specify more interesting things. So as you saw here, that the 7, whether 7 is in the array, that feels like artificial secret, because it's not really about 7, right? Yeah. So I think that could be.
You really want to specify that it's a k prime. K prime is not equal to key,
right,
which is in the array.
Yeah.
So I'm wondering if you can eliminate those quantifiers altogether using the same trick that you did for the data independent variables?
Yeah, that's possible. So in fact, we have also started looking at if you have an unbounded array where the elements of the array are from an unbounded data domain, but the only way you can access these are by equality or order, are properties like reachability, confidentiality desirable for these programs? And we have some results on that, yeah. So
Have you published those papers?
yes, yeah. I mean, it just it's accepted, yeah. So the I think there is actually there is this whole line of work in database literature on automata and logics for data words, which is basically, for example, you may have a tree nodes labeled with data, and the only interesting thing you are doing with this data is doing equality tests and order tests. So automata over such words or trees, under what restriction they are desirable. So there is this whole line of work in database theory also.
But I mean, it's more, I mean, the kind of restriction that you're talking about, if you're just checking the validity question,
Yeah.
Aaron Bradley had a result about it, where he had this restriction that you cannot do arithmetic on the contents of arrays, and you can do some amount of arithmetic on the index variables.
Yeah.
Then you can decide implication. So you can do, precondition-based reasoning. But if you want to do reachability, then you have to do something more than that. Right?
Yeah.
Then you have to achieve closure, right?
Right.
And-
So it's not. Yeah, that's a good point. So there are results in the theory of arrays. So this is different. This is really executions of programs manipulating arrays,
Right.
where the array is unbounded. Yeah. But basically, an unbounded array, you can think of it as a word over an unbounded alphabet. And so then a single loop is really like an automaton which goes over this, and suppose all the other variables were Boolean, then the values of those variables would be like the state of the automaton.
Yes. I mean, this is the kind
Yeah.
of thing that, regular model checking guys have been pushing on for many years, right? There's lots of papers in CAV where they model configurations as automata and transitions as automata transducers, and then they do closure based on that. It's like that, right?
That's also right, but but typically they don't have guarantees about when it would reach fixed points. So here I think there is one could go even more, and in fact the array is not being manipulated. So in all of these, the array is not being updated. The address book is not being updated. So in fact, these protection domains for these devices actually ensure that the things like read-write accesses can be enforced using those. But what they can't enforce is that once you get a read access, which you do need for legitimate reasons, whether you are using it for some other surreptitious purpose,
So
that they don't enforce
the
it.
array is not being updated maybe might be very crucial
For
in
the
getting
for
these,
the decidability
decidability
results.
results. Yeah, that's good.
Three questions or remarks. The first is the information flow has been checked with verification, that is with verification techniques.
Yeah.
And Rajiv Joshi and I wrote a paper in 1997, 98.
Okay.
That describes how to do that. And you have to, we could do non-deterministic programs as well. But you have to, in order to allow the user to write a loop invariant, so you don't need the weakest precondition of a loop computing the exact fixed point, then we had to go to deterministic programs to figure out how to do that, which is described in the journal version of that paper. It also describes the abstraction that you do going to a predicate, like using the predicate for a secret. Then the second thing is, you seem to be, pretty worried about decidability, or maybe it was just, some results that you were able to prove, but
Right, those two were somewhat separate strands, right? Yeah.
Okay, right. So
here I think for this tool, I think the interesting thing would be to get rid of this quantifier alternation and reduce it to satisfiability.
Right, I was going to say, once once you allow loop invariance, or you abstract the loop iterations by invariance, or if you allow calls, procedure calls, and you reason about those in terms of the specifications, then you're going to have quantifiers creep into the weakest precondition computations. So if you have quantifiers and you have arithmetic and so forth, then
I think they're not going to be
right, then the decidability may not be as important. Okay, the third thing is I'm a little bit saddened that you've built the green box here and didn't build on Boogie, which would have let you. That does that for you.
Okay.
Well, of course, you have to instrument it to get it to do what you want to do. But all the translation during the weakest precondition calculations and inlining of calls or loop iterations or using loop invariance, whatever. That's all.
And it works for Vala. For Java.
You'd have to write that translation yourself, or you can use it for spec chart, and the translation is given for you. Was another one of this. But the back end, which computes all the things and gives you the formula that you'd like to pass to the prover, that's provided. And then you can go to not yes-based prover, but
yes. So if we want, if I have to really take this idea and build it into a robust tool, that would be the way to go. Well, I think this is also a good way for students to learn what's involved. Yeah, to try to build it yourself and find out how complex it is, and yeah.
I'm thinking about a scenario where you have a table of name and, for example, nationality pairs.
Yeah.
So the secret is whether John is from Britain, for example.
Okay.
So by going through that array, if I can iterate John with other nationalities, I will be able to figure out whether John is from Britain, right? Without.
Then actually this tool should be, well, I don't know if the tool as such would work, but I'm sure the answer to the question is no, that the program is not secret, because you can't produce an execution, you can't produce an input where the secret does not hold, right? Yeah. No, to show that something is secret.
John is not from India, and then I can iterate this kind of John and non-Britain nationality. Then eventually I will figure out that John is from Britain.
Right, but then the program you would have to analyze is that, let's say there are 6 countries and you have 5 loops, right? One is checking whether John is from India and so on, right? So you have these 5 loops, but for that program you won't be able to show an input array where you need to show 2 input arrays where in one the observation is the same in both cases, and one in which John is from Britain and one in which John is not from Britain. Now to create that input instance when John is not from Britain, you would have to assign John some nationality, and so in that case, that other copy would fail, or it would. What it would not do is that the program you are analyzing is just checking something, and by repeatedly executing that program with different input values, by multiple executions you infer something. That's not handled in this framework. Okay, so I would like the I'll talk to you about that, the reference to that, the work that you mentioned. Yeah, it's quite possible that people rediscover things every 10 years or 20 years. It's maybe it's
something that you do. What we had to do there was to prove the equivalence of 2 programs. What you're showing is the difference of 2 programs. I'm wondering. mean, that may make a huge difference actually, but I don't know. That is in the step towards something that's easier or better to use or can handle more programs. Because you're proving that one program leads to the secret and the other one to the not secret. It'd be interesting to hear.
Okay, thanks.
Okay.